Hello, everyone, and welcome to Coffee with Chloe in the afternoon. So, we are live once again, and I'm back to one of my old series. As you can see, I actually sadly skipped an entire chapter. I'm gonna go back and take some quick notes on block cipher modes. I think I actually might even have these notes somewhere else on block cipher modes. Whatever. But for now, we're just going to dig right in. I'm so far behind on my readings. It's been a crazy couple of weeks. My grandmother passed away a couple weeks ago, like right after our first lesson. Our second lesson happened, and then we had the first funeral a couple days ago. We have a second funeral in a couple of weeks. So things have been pretty busy, but I'm going to try my best just to take more efficient notes, and I'm going to try and to take notes for what I would want to put on the Uncloak website. So, for example, if someone had no clue what a hash function was, I'd probably want to get just something like this. And honestly, actually, I don't even want to talk about its use. Actually, I will talk about its use in digital signatures. And so for example, I could see this being maybe just like the first thing that's written about on Uncloak when you read about hash functions, maybe something similar to this, and then a link out to digital signatures, and we can talk about digital signatures another time. So again, just for me, super high level, and I'm going to go back to taking notes from a very high level, just in bullet point, and I'm literally just going to have my computer read it out. So I'm just going to highlight this. I'm going to say, oops, I am going to highlight the entire thing. And I'm just going to say, read aloud the selected text. For my audio, it should be going to, yes, external headphones, which are my very big speakers here. And so hopefully this goes relatively well. Let's see.
A hash function is a function that takes as input an arbitrarily long string of bits or bytes and produces a fixed size result. A typical use of a hash function is digital signatures. Given a message M, you could sign the message itself. However, the public key operations of most digital signature schemes are fairly expensive in computational terms. So instead of signing M itself, you apply a hash function H and sign HM instead. The result of H is typically between 128 and 1024 bits compared to multiple thousands or millions of bits for the message M itself. Signing HM is therefore much faster than signing M directly. For this construction to be secure, it must be infeasible to construct two messages M1 and M2 that hash to the same value. We'll discuss the details of the security properties of hash functions below. Hash functions are sometimes called message digest functions, and the hash result is also known as the digest or the fingerprint. We prefer the more common name hash function, as hash functions have many other uses besides digesting messages. We must warn you about one possible confusion. The term hash function is also used for the mapping function used in accessing hash tables, a data structure used in many algorithms. These so-called hash functions have similar properties to cryptographic hash functions, but there is a huge difference between the two. The hash functions we use in cryptography have specific security properties. The hash table mapping function has far weaker requirements. Be careful not to confuse the two. When we talk about hash functions in this book, we always mean cryptographic hash functions. Hash functions have many applications in cryptography. They make a great glue between different parts of a cryptographic system. Many times when...
There you go. So that's the first page done. And generally, I've gone through this information previously. I'm trying to just get the pages to line up relatively well. And I'll just do my best to take notes of things that I just feel I should be remembering. And obviously, the sad part is a lot of this isn't formatting the same way. So, H probably needs to have, formatting around it. I didn't even check to make sure the audio is working, but from my monitor, it seems like the audio is working. I always do it to check, but I don't have my phone on me right now again. So just, again, I'm trying to take less notes and just really focus on high-level information to where if you've never heard of hash functions before, what is the basic note you would need just to understand, what they are. So it's a function that takes an input an arbitrary long string of bits or bytes and produces a fixed size result or output. It's using digital signatures. So the result of the hash function, let's see if that was correct, if it's supposed to be hashed. Yeah, the result of the hash function is typically between 128 and 1024 bits, compared to the multiple thousands or millions of bits in the message M itself. Signing H of M is therefore much faster than signing the message directly, and the hash is, specific. So yeah. Okay, so simple enough. Let's keep this relatively short for now, and we'll see. Yeah.
You have a variable size value. You can use a hash function to map it to a fixed size value. Hash functions can be used in cryptographic pseudo-random number generators to generate several keys from a single shared secret. And they have a one-way property that isolates different parts of a system, ensuring that even if an attacker learns one value, she doesn't learn the others. Even though hash functions are used in almost every system, we as a community currently know less about hash functions than we do about block ciphers. Until recently, much less research had been done on hash functions than block ciphers, and there were not very many practical proposals to choose from. This situation is changing. NIST is now in the process of selecting a new hash function standard, to be called SHA-3. The SHA-3 hash function selection process is proving to be very similar to the process that selected the AES as the new block cipher standard.
Okay, and then I'm trying to keep my notes somewhat in order, so I am trying to have order here, but I'm trying to just take less of them and just keep it very basic. They have a one way, so if someone reads this, they should know a little bit of what hash functions are. Previously, I was doing a lot more. I still think this, like Serpent here, you'd still have to go back to the textbook, honestly, to write an article on any of this. But in my opinion, it's already extracted like the highest level information. And so for me, if I had to look back on it, like what's two fish? Okay, so I can actually just high level remember, okay, this is what two fish is. Uses the fight. Anyways, I'm remembering it slowly as I read. So security of hash functions. I'm not going to try and read it. I do not like doing that. It's much more efficient if I just do this. It keeps me going, and then so.
As we mentioned above, a hash function maps an input M to a fixed size output HM. Typical output sizes are 128 to 1024 bits. There might be a limit on the input length, but for all practical purposes, the input can be arbitrarily long. There are several requirements for a hash function. The simplest one is that it must be a one-way function. Given a message M, it is easy to compute HM. But given a value x, it is not possible to find an M such that HM equals x. In other words, a one-way function is a function that can be computed but that cannot be inverted, hence its name. Of the many properties that a good hash function should have, the one that is mentioned most often is collision resistance. A collision has two different inputs M1 and M2 for which HM1 equals HM2. Of course, every hash function has an infinite number of these collisions. There are an infinite number of possible input values and only a finite number of possible output values. Thus, a hash function is never collision-free. The collision resistance requirement merely states that although collisions exist, they cannot be found. Collision resistance is the property that makes hash functions suitable for use in signature schemes. However, there are collision-resistant hash functions that are utterly unsuitable for many other applications, such as key derivation, one-way functions, etc. In practice, cryptographic designers expect a hash function to be a random mapping. Therefore, we require that a hash function be indistinguishable from a random mapping. Any other definition leads to a situation in which the designer can no longer treat the hash function as an idealized black box, but instead has to consider how the hash function properties interact with the system around it. We number our definitions globally throughout this book.
See, and to me, this is pretty straightforward, at least for trying to I don't know. I feel like recently my main goal is just to keep track of what I'm trying to learn.
Definition 4. The ideal hash function behaves like a random mapping from all possible input values to the set of all possible output values. Like our definition of the ideal block cipher, section 3.3, this is an incomplete definition. Strictly speaking, there is no such thing as a random mapping. You can only talk about a probability distribution over all possible mappings. However, for our purposes, this definition is good enough. We can now define what an attack on a hash function is. Definition 5. An attack on a hash function is a non-generic method of distinguishing the hash function from an ideal hash function. Here, the ideal hash function must obviously have the same output size as the hash function we are attacking. As with the block ciphers, the non-generic requirement takes care of all the generic attacks. Our remarks about generic attacks on block ciphers carry over to this situation. For example, if an attack could be used to distinguish between two ideal hash functions, then it doesn't exploit any property of the hash function itself and it is a generic attack. The one remaining question is how much work the distinguisher is allowed to perform. Unlike the block cipher, the hash function has no key, and there is no generic attack like the exhaustive key search. The one interesting parameter is the size of the output. One generic attack on a hash function is the birthday attack, which generates collisions. For a hash function with an n-bit output, this requires about 2 steps. But collisions are only relevant for certain uses of hash functions. In other situations, the goal is to find a preimage given x, find an m with h m equals x, or to find some kind of structure in the hash outputs. The generic preimage attack requires about 2 steps.
Ooh.
We're not going to discuss at length here which attacks are relevant and how much work would be reasonable for the distinguisher to use for a particular style of attack.
And this is already known.
To be sensible, a distinguisher has to be more efficient than a generic attack that yields similar results. We know this is not an exact definition, but as with block ciphers, we don't have an exact definition. If somebody claims an attack, simply ask yourself if you could get a similar or better result from a generic attack that does not rely on the specifics of the hash function. If the answer is yes, the distinguisher is useless. If the answer is no, the distinguisher is real. As with block ciphers, we allow a reduced security level if it is specified. We can imagine a 512-bit hash function that specifies a security level of 128 bits. In that case, distinguishers are limited to 2,128 steps.
Could be helpful. Like, to me, it's straightforward, but I'm gonna forget. It is something I would definitely. I'm not sure if it matters to remember that though, but whatever. Real hash functions, okay. So I'll just, there are very good hash functions out there at this moment. You are pretty much stuck with the existing SHA family. And again, this is written 10 years ago, so I think SHA-3 is most people use now. I'm not sure. There are other published proposals, including the new SHA-3 standard. So I think I've seen SHA-3 used, or KCAC 256 or whatever used. I think KCAC is, I guess, newer, obviously, but we'll see. So.
Submissions for the new SHA-3 standards, but these all need to receive more attention before we can fully trust them. Even the existing functions in the SHA family have not been analyzed nearly enough, but at least they have been standardized by NIST, and they were developed by the NSA.1. Almost all real-life hash functions, and all the ones we will discuss, are iterative hash functions. Iterative hash functions split the input into a sequence of fixed-size blocks M1. MK, using a padding rule to fill out the last block. A typical block length is 512 bits, and the last block will typically contain a string representing the length of the input. The message blocks are then processed in order, using a compression function in a fixed-size intermediate state.
Cool.
This process starts with a fixed value h0 and defines I equals hi minus 1 mi. The final value hk is the result of the hash function.
Cool.
Such an iterative design has significant practical advantages. First of all, it is easy to specify and implement compared to a function that handles variable length inputs directly. Furthermore, this structure allows you to start computing the hash of a message as soon as you have the first part of it. So in applications where a string of data is to be hashed, the message can be hashed on the fly without ever storing the data. As with block ciphers, we will not spend our time explaining the various hash functions in great detail. The full specifications contain many details that are not relevant to the main goals of this book.
So yeah, I like that how, again, just like, obviously giving a high-level overview. My notes for now is just pulling out exactly what I would have to remember to try and actually go back through this and write like an article about this. And I guess that's the idea as well, right? Like, if I just have this written down, how could I take this information and then other information to write an article at some point? And so that's what I'm trying to only get now, is like just like article writing support, if that even makes sense. So again, like, I'm not even sure if a simple but interesting hash function, like, I probably wouldn't word the article that, or title the article that, but the idea is, I guess, to try and come up with articles that not only I could write, but maybe other people could write. Again, if we have a hackathon, MarvaJCon, maybe someone can read these notes going through this article and goes, okay, you know what? I could write an article on hash functions. Here's some notes, here's a textbook. You can obviously use Wikipedia and other textbooks and stuff like that as well. But
before discussing real hash functions, however, we will begin by giving an example of a trivially insecure iterative hash function. This example will help clarify the definition of a generic attack.
Okay.
This hash function is built from AES with a 256-bit key. Let K be a 256-bit key set to all zeros.
Okay.
To hash the message, first pad it in some way and break it into 128-bit blocks M1. MK, the details of the padding scheme aren't important here. Set H0 to a 128-bit block of all zeros. And now compute high equals AESK, high minus 1 MI. Let HK be the result of the hash function. Is this a secure hash function? Is it collision resistant?
Okay.
Before reading further, try to see if you can find a way of breaking this hash function yourself.
Oh. Did it? No. Why did it really want to do that? So rude. Oh god. I gotta like zoom in 100 times again. So yeah, I just wanted to like actually obviously read it a little bit slower than what I was doing. Okay. So AES with a 256-bit key. I don't have like an AES diagram in front of me, so I could go through my notes and search up AES. Okay, that's helpful. So let K be a 256-bit key set to all zeros to hash the message. First pad it in some way. Okay, we pad it, fine. And break it into 128-bit blocks. M1 to M the size of the key. 128-bit blocks. The details of the padding scheme aren't important. Okay. Set H 0 to 128-bit block. So I get, okay, of all zeros. It's a hash. Okay, so now compute, if you just do some hash using AES with a key of all zeros. H 0 minus 1 XORed with the message, which will be the same as the key. Man, I don't know. This is complicated. Why are you asking me these hard questions for? Anyways, let's keep going. See if I can find a way of breaking the hash. So HK is the result of the hash function. I might understand what it's talking about. AES of K. H. Is it just because they're all zeros? Like, yeah. Okay, now here's a non-generic attack. Fine, maybe it's just going to explain it to us now. Pick a message M such that after padding, it splits into 2 blocks. M1 and M2. See, I don't get, like... Is it just saying that we're... I just think that, I mean, I'm not clear what the fuck they're talking about. Anyways, you have M1 and M2. That's clear enough. Let H1 and H2 denote the values computed as part of the hash function's internal processing. Sure. So the hash function just spits out H1 and H2. Sure. H2 is the output of the hash. Okay, so H2 is the output at least. That's fine. Now let M1 prime or M whatever equal M2 XORed with H1, so some piece of the hash function. Again, let M2 prime be the output of the hash function XORed with the second half of the message, so the padding, guessing is all zeros, like it doesn't matter how you pad it, XORed with this other part of the hash function, and let M prime be the message that splits into M1 prime and M2 prime after padding. Okay. Due to properties of the hash function's construction, M prime also hashes to the output. Okay. You can verify this in the exercise at the end of the chapter. Okay. That's not anyways. And with very high probability, M and M prime are different strings. That's right. M and M prime are two distinct messages. I learned nothing from that personally. But that's just probably, maybe I'm just terrible at algebra. So that could just be, the issue there. Let's continue. That was not, I'm just going to that was not helpful. MD5 though, I think, I've already read through this. This was actually helpful to read through and understand hash functions. I don't know why they added that. I feel like if it's pure math, I understand it. And if it's pure, this is an efficient construction, I understand it. But when, textbooks try and, be witty and, show me why something is, oh, look at this not efficient thing. And I'm always my brain, I don't know, I'm always just I don't get it. I don't get. But if it's just explain, I love, YouTube videos for this, where I'm just, explain to me this, number theory topic or whatever. And I'm okay, I'm getting there. I need to do more math stuff. I haven't gone through math lectures in 3 weeks. 3 weeks at least. Oh my god,
Let's now turn to some real hash function proposals, beginning with MD5. MD5 is a 128-bit hash function developed by Ron Rivest 104. It is a further development of a hash function called MD4 106 with additional strengthening against attacks. Its predecessor MD4 is very fast but also broken 36. MD5 has now been broken too. You will still hear people talk about MD5, however, and it is still in use in some real systems.
I'm not sure it's still that
much in use.
The
first step in computing MD5 is to split the message into blocks of 512 bits. The last block is padded and the length of the message is included as well. MD5 has a 128-bit state that is split into 4 words of 32 bits each. The compression function H has 4 rounds, and in each round the message block and the state are mixed. The mixing consists of a combination of addition, XOR, and OR, and rotation operations on 32-bit words. For details, see 104. Each round mixes the entire message block into the state, so each message word is in fact used 4 times. After the 4 rounds of the H function, the input, state, and result are added together to produce the output of H. This structure of operating on 32-bit words is very efficient on 32-bit CPUs. It was pioneered by MD4 and is now a general feature of many cryptographic primitives. For most applications, the 128-bit hash size of MD5 is insufficient. Using the birthday paradox, we can trivially find collisions on any 128-bit hash function using 264 evaluations of the hash function. This would allow us to find real collisions against MD5 using only 264 MD5 computations. This is insufficient for modern systems, but the situation with MD5 is worse than that. MD5's internal structure makes it vulnerable to more efficient attacks. One of the basic ideas behind the iterative hash function design is that if H is collision resistant, then the hash function H built from H is also collision resistant. After all, any collision in H can only occur due to a collision in H. For over a decade now, it has been known that the MD5 compression function H has collisions 30. The collisions for H don't immediately imply a collision for MD5. But recent cryptanalytic advances, beginning with Wang on U124, have now shown that it is actually possible to find collisions for the full MD5 using much fewer than 264 MD5 computations. While the existence of such efficient collision-finding attacks may not immediately break all uses of MD5, it is safe to say that MD5 is very weak and
I think
should
this
no
is
longer be
important
used.
because the paper obviously that can be read here. I mean, it's not even going to link out properly for us, but I'll leave it there. Okay, Shaw 1. Again, just things that are actually used. I think my dog is missing me or something. He's outside of the door crying. Poor baby. Okay. I think I read all this on the plane already when I was flying from Antigua. Does it not want to read anymore? Maybe not. That'd be a bit sad. Let's see. Boom, 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 boom. We're gonna hope it just starts working. I mean, it's only been about half an hour. I want to at least go for another half an hour. Would be great. Shaw 1. Drop frames 0. I could just read it, obviously, but it's no fun in that. Obviously, I might have to. Oh, this pushes the words over a bit. Nice. Maybe something's wrong with the headphones. I don't really feel like closing anything. Like, I might just read it. The whole point, though, is that it's no fun. Cannot access extension manifest, must request permissions. Oh, the extension's having issues. Yeah, extension's having issues. Access requested. To give it access, click it. Yeah, it's having some sort of issues. We're trying. We could just like close the extension, turn it back on. That should probably. Okay, maybe working now. Let's see. Maybe not, to be fair, and then that might just be it telling me to go do something else. It's weird how even if I could do the whole remove from Chrome thing and put it back on. Because it's obviously having a lot of issues. Let's do it. Remove from Chrome. Remove. I should have like opened it first, right? Where's the... Nope. Oh, it really wants to... There we go. Cannot read aloud this website. Maybe it's because I'm not using US English Female TTS by Google. That could be the issue, apparently. Okay. That's interesting. I'll bite. Oops. This is just not what I'm looking for. I think I just closed the whole thing. Oh, this is the same tab. Okay. Bruce. Nope. I'm having a tough time with this one. Open with Google Chrome. And this should hopefully start working, but apparently the issue was the voice choice, which I find to be very interesting. So I'll try and there we go. Now, after all of that, let's see if we got that working. And if not, how do I, options. No, there we go. Voice. Where is it? English, Google. It was some Google thing. Okay, let's go back to this English Google person. If not, I mean, I'll just read this somewhere else. I'm not going to stream myself talking. Yeah, so I guess maybe that's it for the live. On my other devices, this is so much easier. My tablet and everything else. I just seem to time out, try picking another voice. Apparently some voices just don't work very well. Albert?
Legge ad alta voce è un'estensione per Chrome e Firefox che utilizza la tecnologia di sintesi vocale.
What?
Läs högt är ett Chrome och Firefox-tillägg som använder.
Andalou est une extension Chrome et Firefox qui utilise la technologie de synthèse vocale.
Read Aloud ialah sambungan Chrome dan
Is this supposed to not be English?
Read Aloud ist eine Chrome- und Firefox-Erweiterung.
Is it just reading? Okay, wait. Is it reading English in a different language because I used... Okay, one second.
De Securage algorithme was designed by the NSA and standardized by NIST. 97. The first version was just Khaled SHA, one of Khaled SHA 0. The NSA found weakness with SHA 0, and the developed a fixed published an improved version, Khaled SHA 1. And, Teddy not release any details of the weakness. 3 years later, SHA 1 and published a weakness on SHA 0, 25. This weakness is fixed by the improved SHA 1, so it is reasonable to assume time no what the problem was. SHA 1 is a 160 bit hash function based on MD4. Because of its shared parentage, it has a number of features in common with MD5, but it is a far more conservative design. It is also slow with MD5. Unfortunately, despite a more conservative design, we don't know that SHA 1 is also insecure. SHA 1 has 160 bits that consisting of 532-bit words. Like MD5, it has 4 that consist of a mixture of elementary 32-bit operation. Instead of processing hash message block 4 times, SHA 1 use a linear recurrence to stretch the 16 words of a message block to the 80 words it may end. This is a generalization of the MD4 technique. In MD5.
What is happening right now? That was like half French, half not French. It just translated the English textbook into French. I'm like, okay, so if I just took this, like it's actually in French.
The Securage algorithm was designed by the NSA and standardized by NIST.
Like it's translating the words. I don't know why. but it's legitimately translating it to French. And so I just need to find one of these people that speaks English. I'm so...
Read aloud adalah ekstensi Chrome dan Firefox.
It's just different.
Read aloud is a Chrome and Firefox extension that uses text-to-speech technology to convert webpage text to audio. It works on a variety of websites.
But can we just get like a normal... Daniel's fine.
It works on a variety.
No, I want something a little more normal, maybe. Like...
To read aloud in een epecta to Chrome to
Read aloud Shigiga Chrome Firefox.
We might have to use Daniel.
Read aloud je prošíreně zachr. Čítať nahlas je
This is
rozšírenie
wild.
pre
This
premia.
is not... Oh, sorry, not Finnish. No, English. So this... Okay, so the normal English US female doesn't work. How about... English. What? Oh my gosh. Google should have worked, I guess. Grandma?
Read aloud is a Chrome with Firefox extension that uses text-to-speech tech. Read aloud is a Chrome with Firefox extension that uses text-to-speech technology to convert
It just
web
sounds really weird.
It works on a variety of websites, including news sites, blogs, fan fiction,
Daniel might,
textbooks,
like...
course materials.
Read aloud is a Chrome and Firefox extension that uses text-to-speech technology. Read aloud is a Chrome and Firefox extension that uses text-to-speech technology to convert webpage text to audio. It works on a variety of websites, including news sites.
Yeah, I think it I think it has to be Daniel. You know.
Read aloud is a Chrome and Firefox extension that uses text-to-speech technology to convert webpage text to audio. It works on a variety of websites, including news sites, blogs, fan fiction,
Not happy about
school and
this.
course materials.
Not happy about it, but...
The secure hash algorithm was designed by the NSA and standardized by NIST. 97. The first version was just called SHA, now often called SHA-0. The NSA found the weakness with SHA-0 and developed a fix and NIST published as an improved version, called SHA-1. However, they did not release any details about the weakness. 3 years later, Chadwell and Jantz published a weakness of SHA-0. 25. This is a weakness that is fixed by the improved SHA-1, so it is reasonable to assume that we now know what the problem was. SHA-1 is a 160-bit hash function based on MD4. Because of its shared parentage, it has a number of features in common with MD5, but it is a far more conservative design. It is also slower than MD5. Unfortunately, despite its more conservative design, we now know that SHA-1 is also insecure. SHA-1 has a 160-bit state consisting of 5 32-bit words. Like MD5, it has 4 rounds that consist of a mixture of elementary 32-bit operations. Instead of processing each message block 4 times, SHA-1 uses a linear recurrence to stretch the 16 words of a message block to the 80 words it needs. This is a generalization of the MD4 technique. In MD5, each bit of the message is used 4 times in the mixing function. In SHA-1, the linear recurrence ensures that each message bit affects the mixing function at least a dozen times. Interestingly enough, the only change from SHA-0...
It's too fast. They improved it, SHA-1 did all of this, only thing they changed. There you go. I'm just gonna write that for now. Okay, and then... Okay, so there's also a way to actually attack SHA-1 anyways, so not too big of a deal. We can go into those things later. Whoops. Sure. Let's go, Daniel. Fine.
In 2001, NIST published a draft standard containing 3 new hash functions, and in 2004 they updated this specification to include a fourth hash function 101. These hash functions are collectively referred to as the SHA-2 family of hash functions. These have 224, 256, 384, and 512 bit outputs, respectively. They are designed to be used with the 128, 192, and 256-bit key sizes of AES, as well as the 112-bit key size of 3DES. Their structure is very similar to SHA-1. These hash functions are new, which is generally a red flag. However, the known weaknesses of SHA-1 are much more severe. Further, if you want more security than SHA-1 can give you, you need a hash function with a larger result. None of the published designs for larger hash functions have received.
Okay, this I guess relatively important. Well, they're not really new anymore, so. Okay. This is probably more important potentially. Did I? Oh yeah, these are all supposed to have another. A fourth one. If there's 3, they need 4. If there's 2, they need 3. So this one's 3 because it has 2. 4. Am I messing this up? No. Yeah. 1 has 2. Perfect. Sorry. Unfortunately, my back needs to be cracked. All of these functions have some properties that disqualify them according to our security definition. Okay. Ooh, this is fun. Ooh, this is fun. And then it's exercises already. Nice. I feel like I read this whole thing on the plane, potentially, but still a fun chapter.
Our greatest concern about all these hash functions is that they have a length extension bug that leads to real problems and that could easily have been avoided.
Oh,
Here is
they
the
all
problem.
have.
A message n is split into blocks n1, mk and hash to evaluate. Let's now choose a message n that splits into the block n1, mk plus 1. Because the first k blocks of m are identical to the k blocks of message m, the hash value h, m, is nearly the intermediate hash value after k
Why
blocks.
does that still sorry, I did not mean to do that. It still seemed too fast. Maybe Daniel...
Read Aloud is a Chrome and Firefox extension that uses text-to-speech technology to convert web page text to audio. It works on a variety of websites, including news sites, blogs, fan fiction, publications, textbooks, school and course materials.
I think Daniel just talks faster, potentially. Maybe I'm just getting tired. So, sorry. Hopefully last time I'll have to do that. And we can just... But I was not retaining any of that information. Yeah, I would definitely like to remember what I'm listening and reading to.
Our greatest concern about all these hash functions is that they have a length extension bug that leads to real problems and that could easily have been avoided. Here is the problem. A message n is split into blocks n1, mk and hash to evaluate. Let's now choose a message n that splits into the block n1, mk plus 1. Because the first k blocks of m are identical to the k blocks of message m, the hash value h, m, is nearly the intermediate hash value after k blocks in the computation of h, m. We get h, m, equals h, m, mk plus 1. When using MD5 or any hash function from the SHA family, you have to choose m carefully to include the padding and length field. But this is not a problem as the method of constructing these fields is known. The length extension problem exists because there is no special processing at the end of the hash function computation. The result is that h, m, provides direct information about the intermediate state after the first k blocks of m. This is certainly a surprising property for a function we want to think of as a random mapping. In fact, this property immediately disqualifies all of the mentioned hash functions. According to our security definition, all a distinguisher has to do is to construct a few suitable pairs, m, and check for this relationship. You certainly wouldn't find this relationship in an ideal hash function. This is a non-generic attack that exploits properties of the hash functions themselves, so this is a valid attack. The attack itself takes only a few hash computations, so it is very quick. How could this property be harmful? Imagine a system where Alice sends a message to Bob and wants to authenticate it by sending H, XM, where X is a secret known only to Bob and Alice, and M is the message. If H were an ideal hash function, this would make a decent authentication system, but with length extensions. Eve can now append text to the message M, and update the authentication code to match the new message. An authentication system that allows Eve to modify the messages, of course, of no use to us.
I just realized something very sad. When I copy and paste the primes into Obsidian, it doesn't paste the primes. So it's gonna be really I really have to go back and a little more often than I have been doing, if it's not even doing the primes. I thought I was gonna at least be able to write it all at one time and then go back and edit it later. Still might be able to, but there's no way I'll be able to remember where the primes went. I could put formatting around things, but I'm sure I'm missing a whole bunch of context in all of this. So it is what it is. I'm gonna have to go back, but let me at least finish the chapter and let me maybe just take the ones down where I'm at. So the length extension. So greatest concern, length extension bug. So basically, message M is split into blocks, M 1 to M all the way to the length of the key, I guess, and hashed into a value H. Okay. Let's now choose a message, a different message that splits into the block M1 to MK, like before, but you're actually gonna go long, extend beyond the current message. Because the first K blocks of this new message are identical to the K blocks of the original message, the hash value hash of M is merely the intermediate hash after K blocks of the computation of H of this new message, the hash of this new message. We get the hash of the new message actually equals this other hash of the hash of the first message hashed with the message of K plus 1, like the extension. Ooh, so okay. So when using MD5 or any hash function from the SHA family, you have to choose M prime, your other message, carefully to include the padding and length field. But this is no problem, as the method of constructing these fields is known, so someone else could just construct the fields the same way. The length extension problem exists because there's no special processing at the end of the hash function computation. The result is that, okay, let's try and get it properly here. Okay, this one's simple. H of M provides direct information about the intermediate state after the first K blocks. Let's go here of M prime. And I'm probably just going to go back now and do it because it seems like I might be able to just see where there's a space. And wherever there's a space in my... There's not even much, actually. I didn't copy and paste much math. Here, though. So... This actually all looks fine. Like, there wasn't very many prime stuff. Yeah, actually, this looks fine. Cool. Sorry, I'm probably really close to the screen. I think there was a spacing there every time there was the prime that had to be there. Okay, maybe that one's wrong. So let's go to 5.1 real quick to see if that's an issue. Just, okay. No, yeah. Find a pre-image. Why am I having such a hard time finding where this was? Collision resistance. Yeah, it's just find an M. Right? 5.1. Oh, this is at the end. Sorry, this is after this. I was like, what the heck is going on? Yeah, here. Pre-image, given X, find an M. Given X, find an M with H of... Yeah, all that's fine. There was no issues here. It got more complicated later, and I realized it right away. Just making sure. Awesome. We get this. Okay, the length, blah, blah. This is a present property. In fact, the property really describes all the message values according to description. All this message is find. Okay, yeah. Okay, this property does this. All you have to do is do this. Okay, and you wouldn't find that in an ideal hash function. Okay. And I do have to... I mean, I will just... prime. Okay, you wouldn't find that in an ideal hash function. It's a non-generic attack that exploits the hash function themselves, so it's valid. The attack itself takes a few hash computations, so it's very quick. How could it be harmful? Imagine a system where, of course, I think it's pretty obvious why it's harmful. The issue is resolved in SHA-3. Basically, one of the requirements is that it doesn't have length extension properties. Okay. Oh, it doesn't even... Okay. I thought it would have, like... Anyways. I guess it's just like more attacks, I guess, and like why things were unsafe. I would have rather just went straight into SHA-3, but partial measure. They're just talking about more, I guess, weaknesses now though, so yeah, let's just read through it, I guess. Whoops. Having issues. Let's go, Daniel.
A second problem is inherent in the iterative structure of most hash functions. We'll explain the problem with a specific distinguisher. The first step of any distinguisher is to specify the setting in which it will differentiate between the hash function and the ideal hash function. Sometimes this setting can be very simple. Given the hash function, find a collision. Here we use a slightly more complicated setting. Suppose we have a system that authenticates a message M with H, MX, where X is the authentication key. The attacker can choose the message M, but the system will only authenticate a single message. 2 for a perfect hash function of size n. We expect that this construction has a security level of n bits. The attacker cannot do any better than to choose an M, get the system to authenticate it as H, MX, and then search for X by exhaustive search. The attacker can do much better with an iterative hash function. She finds 2 strings M and M that led to a collision when hashed by H. This can be done using the birthday attack in only 2n/2 steps or so. She then gets the system to authenticate M, and replaces the message with M. Remember that H is computed iteratively, so once there is a collision and the rest of the hash inputs are the same, the hash value stays the same, too, because hashing M and M leads to the same value, H, MX, equals H, MX. Notice that this attack does not depend on X. The same M and M would work for all values for X. This is a typical example of a distinguisher. The distinguisher sets its own game, a setting in which it attempts an attack, and then attacks a system. The object is still to distinguish between the hash function and the ideal hash function, but that is easy to do here. If the attack succeeds, it is an iterative hash function. If the attack fails, it is the ideal hash function.
I mean, yeah, but I feel like I didn't... Sorry. I feel like this is a great example teaching me something. I feel like all I can really note down is like there was some fun math in there, I guess, to explain it, but like this is the problem, that they're iterative. And let's see. Detecting much better. So basically, for a perfect hash function, we expect this. And then the attacker cannot do any better than choose a message and get the exhaustive search. That makes sense. That is very clear. Ooh, doesn't like the character. So for now, I'm just going to double bar it. We can fix it later. Okay. But the idea is the attacker can do much better with an iterative hash function. You find two strings that have a collision. You do birthday attack. Then you set the system to authenticate the message. And you replace the message with M prime. Remember that H is computed iteratively. So once there's a collision and the rest of the hash inputs are the same, the hash value stays the same as well. Because hashing M and M prime leads to the same value, the hash of M with the authentication key and the hash of M prime with the authentication key is the same. Notice the attack does not depend on the authentication key. You just have to attack the hash function. I mean, I guess. I guess this is what they're trying to say. So they're saying because H is computed iteratively, once there is a collision and the rest of the hash puts are the same, the hash value stays the same too. I'm not sure, like, I mean, I get it. That's an attack. And I guess the idea is you can do it in birthday attack steps. So, like, yeah, I guess because you have, okay, like, you could do better, you find this, and you can do it in birthday steps. Let's just keep it simple and move on. I just, again, wanted to make sure I got M prime in there. Whoops. I'll do this one, sure. It's right here. Okay. If the attack succeeds, it's iterative. If the attack fails, it's ideal. Which is a distinguisher, but I guess it also shows you how you would know that there's an ideal. But yeah, that's just... Anyways. Fixing the weaknesses. So I guess, yeah. How do you get rid of this iterative property? 1, 2, 3. Oops. 1, 2, 3. We want a hash function that we can treat as a random mapping, but all well-known hash functions fail this property. Well, we have to check for limitation problems in every place we use a hash function. Do we check for partial message collisions everywhere? Are there any other weaknesses we need to check for? Most systems only offer the message being authenticated. This is just an extreme case. In real life, many systems include a message number weak message, which has the same effect as attack is only allowing single messages to be chosen. Okay. I'm just gonna keep reading it.
Leaving weaknesses in the hash function is a very bad idea. We can guarantee that it will be used somewhere in a way that exposes the weakness. Even if you document the known weaknesses, they will not be checked for in real systems. Even if you could control the design process that well, you would run into a complexity problem. Suppose the hash function has 3 weaknesses, the block cipher 2, the signature scheme 4, etc. Before you know it, you will have to check hundreds of interactions among these weaknesses. A practical impossibility. We have to fix the hash function. The new SHA-3 standard will address these weaknesses. In the meantime, we need short-term fixes.
I don't know. Suppose the hash function has 3 weaknesses. The block cipher, 2. The signature scheme, 4. I don't know why the numbers are here like that. I don't get it, but anyways. Okay, I don't like how it just does it like that, because there's nothing that was said there. Except for like, oh, leaving weaknesses is a very bad idea. Sure, let's just keep it simple. Just so that I can keep track of what that was actually written, and like that's actually a chapter thing. 4. Okay. Okay. Here is one potential solution. Ultimately, we'll recommend the fixes in subsequent subsections, and this particular proposal has not received a review in the community, but this discussion is illustrative, so we can include it here. Okay, this is like a whole like solution. Let's just. I think the definition is all I'm really gonna. Well, let's. Yeah, just the definition probably. Let H be one of the hash functions mentioned above. Instead of the message, just being, not being hashed together, one could use the message and then hash the message concatenated with the message and hash that together as a hash function. Effectively, we put the message hash before the message we are hashing. This ensures that the iterative hash and computations immediately depends on all the bits of the message. Okay, yeah, let's just take the definition down because I feel like that's the only thing here that's going to make any sense. Okay. The hash. I don't even know what that even means. Like, if I do like this and I do lower and I do that, I guess. Cool. It's capitalized. DBL. Why didn't it capitalize? That's so weird. It didn't do it when I copied and pasted it. So again, it's H DBL. M, this little weird thing, HHM, and then this thing, and then I think I can just double bar it, and those double bars are ugly. Okay, no, it fixed it. Cool. Cool. So definitions there. We believe that if H is any of the newer SHA-2, this function has security of n little bits, where n is the size of the hash result. Cool. It's slow. Okay, cool. So this is very clear. It's slow though. You have to hash every time message twice, which takes twice as long. Another disadvantage is that the target approaches the whole message to be buffered. Okay, the whole message to be added on. You can no longer compute the hash of a stream of data as it passes by. Some applications depend on stability, and using HDBL would simply not work. Cool. See that I learned a lot there. That was cool. That explained something to me. Like, oh, you could fix it like this, and I was like, oh yeah, that makes sense. And they were like, oh wait, but that would take like way much more time and effort. And I was like, oh yeah, that too. But it is what it is. So how do we keep the full speed of the original hash function? We cheat, kind of. Instead of hashing the message, we can use the hash of 0 bytes concatenated with the message as a hash function. And claim a security level of half of n. Okay. Oh, the block length. Okay. I was like, what? Okay, so here B is the block length of the underlying compression function. Okay. So 0B concatenating with a message equates to prepending the message with an all. Oh, it is all 0 still, but it's not just 2 bytes or whatever. It's as the size of the compression block before hashing. The cheat is that we normally expect an n-bit hash function to provide a security level of n bits for those situations in which a collision attack is not possible. The partial message collision attacks all rely on birthday attacks, so if we reduce the security level to n over 2 bits, these attacks no longer fall within the claimed security level. In most situations, reducing the security level in this way would be unacceptable, but we are lucky here. Hash functions are already designed to be used in situations where collision attacks are possible, so the hash function sizes are suitably large. If we apply this construction to SHA-256, we get hash functions, okay, which is exactly what we need. Some might argue that all n-bit hash functions provide only n over 2 bits of security, that is a valid point of view. Unfortunately, unless you are very specific about these things, people will abuse the hash function and assume it provides n bits of security. For example, people want to use SHA-56 to generate 256 key for AES, assuming that it will provide a security level of 2 bits. Obviously, it will only be half. Anyways, earlier we used the keys for security, so this matches perfectly with the reduced security level. It is not accidental in both cases. The gap between. Cool. So I think obviously I can just take this down probably. Let's see. Let H be an iterative half function. Let B denote the block and go to a compression function. Okay, so I'm going to take down the definition, but I am going to take down some extra notes because they were actually pretty useful this time. And then the main thing was dual bars and everything else. I think maybe like 0 to the to the power of B, and then H under to D. Honestly, I think I should be able to honestly just put little thingies around the whole thing now and do that. I don't know why it's being weird still, but not my. Oh, okay, that's why. Okay, good enough. Oh, yeah, good enough. We will use construction mostly for hash function from the SHA family for any hash function SHA-X, where X is blah, 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 blah. We define SHA-DX as the function that maps a message to SHA-X, X, D, blah, blah. SHA is just a function of blah, blah, blah. 512, for example. Okay, this is pretty useful in my opinion. There was other notes that I want to put up as well. Like this example here is pretty straightforward. What's the thing? Right arrow. Right arrow, SHA-256, SHA-256, 0 to the power of 512, right arrow, oops, not right arrow, double bar, for example, and then I guess I have to do the other side too. There we go. Oh, right arrow. Oh, there's 2 right arrows. What did I do? Oh, let's delete one of them. M, right arrow, SHA-256, SHA-256, 0 to that with the M, for example. Okay. This particular fixed SHA family of addition being related to recognition was also described by this. It can be determined that the fixed hash function HD is at least as strong as the analytic hash function. HMAC uses a similar hash it again approach to protect against length session attacks. Prepending the message with a block of zeros makes it so that unless something unusual happens, the first block input to the inner hash function D is different than the output. Both HDBL and HD when there's a bug. Whether HDBL in fact has a security level and boost is ready to be seen. We would trust both of them to be up to security. So in practice, we would use the more efficient HD construction. Okay, that's interesting. This is interesting. So I am gonna say that. We already know it's H underscore DBL. I hate that I have to do this whole thing every time. Okay. H underscore D is fine. Okay. And there was stuff up here I kind of wanted to keep in the mix, probably before the definition, just because I found it interesting. So how do we keep the full speed? We cheat. Instead of HM, we use H and we append it with a bunch of zeros with the number of bits as a hash function, and claim only the security of n/2. Here, B is the length of the block. Okay, so I don't think I wrote that down. Yeah, I don't think I even have that written down. I definitely want to get that. So B. Okay. Oh, wait. Let me just put this under, actually, because where K is variable of H and N. Yeah, all this stuff is written out, but I don't see anything about B. So let's just make sure we get that. And so 0. Whoops. So 0 to the power of B. Okay. Okay, then it actually tells you what B is. So if that's helpful, you're claiming a security of, yeah, we already have a security level of min K. K is the security level of H, and N is the size of the hash result. Okay. The cheat is we normally expect an n-bit hash function to provide n bits of for those situations in which a collision action is not possible. So we're cheating, but we're being clear about it. The partial message collision attacks all rely on birthday attacks. So if we reduce the security to n/2, these attacks no longer fall within the claimed security level. Well, look at here. Hash functions are designed to use. Okay. This seems relatively straightforward so far. Just there's like a couple ways to have short-term fixes. Here's one way. Here's a more efficient way, and then we believe in it because we were assuming that everything's only half as safe, and then because of that we can. Oh, there's one more fix. So let me just get another fix in real quick. And then once I get these fixes in, I finish the chapter. I will just end the stream there and go through chapter 6 tomorrow, probably. There's another fix to some of the weaknesses. Truncate the output. If a hash function produces n bits, only use the first n minus s bits. Honestly, for some positive s. In fact, SHA-224 and SHA-384 both already do this. SHA-224 is roughly SHA-256 with some bits dropped. For 252, you could hash 512. This result would be a 250-bit hash function, which, because of birth attacks, would meet are very interesting. This is actually just very straightforward, though. So let's just put that there. I don't even think we would need this for now. Okay, just do that. And then maybe just like the example, because this is pretty cool. Like it makes it very clear how you would actually go about doing it. Okay. Which hash function should I choose? I don't even think, SHA-3 or Kakak at this point, I think, but I like it that, like, again, like this is kind of a title of an article. I could see this being on Uncloak as an article of like which hash function actually. Obviously this was written over 10 years ago, but now maybe you'd have some articles about top ones people are saying now to use and why you might want to use them and how to link to other things. So this is like, again, what I'm thinking of when I'm taking notes here. And so many submissions to the SHA-3 competition have new designs. They address weaknesses. However, the competition is still going, and SHA-3 hasn't been selected. So obviously, I would just say SHA-3 for now. Much additional analysis is necessary. In short term, we recommend using one of these new things. I guess was one of the tricks that were there. Moreover, we suggest you choose a hash function from the SHA family or use SHA D family, with like the fixes, or use SHA 512 and truncate to 256. In the long term, we will very likely recommend the winner of the SHA 3 competition. So SHA 3. Yeah, and then obviously KCAC or whatever later. So simple enough. Exercises, and I'll try and usually, I actually don't put them here. I have another tab here for exercises. As I said, I kind of skipped chapter 4 by accident, or I don't know if it was by accident, but it just didn't happen. 1, 2, 3. Although I don't think I do. I think I do 2. Chapter 3, and I put 3. Yeah, I'll just do that. I'll just do it like that. Use a software tool to generate 2 messages, M and M prime, where M is not the same as, so 2 distinct messages that produce a collision for MD5. To generate this collision, use one of the known attacks against MD5. A link to example code, finding collisions available here. That seems like a useful exercise. Oh, I don't like when that happens at all. Let me just... I'm glad that this textbook makes that straightforward. I think... Okay, I said hopefully last time, and I lied, because it was not the last time. But I think this is an exercise that is at least worth looking at. Next, using an existing cryptographic library, write a program to compute the SHA-512 hash value of the following message in hex. That seems relatively straightforward, right? You're just working with hashing algorithms, and it seems like maybe with OpenSSL, it might be able to do that very easily in the command line with bash, and I'll try and look at that again for this week. I kind of liked doing it that way last time as well. Hex, and then I don't know why it does it like that, but Control X, Control V. Don't know why the formatting comes up like that. Okay, this looks very weird. Right? My friend. Oh, okay, that's good enough, I guess. That's how it... I don't know why it's not showing any color, though. I don't like how it... Rust. Okay. It doesn't like hex today. Okay. That's weird. So, going to exercise 3. Consider SHA-512-N, a hash function that runs SHA-512 and then outputs only the first N bits. Okay. So it's truncated. Write a program that uses a birthday attack to find and output a collision on this bad boy, where N is a multiple of 8, between 8 and 48. Your program may use an existing cryptography library. Time how long your program takes when N is 8, 16, 24, 32, 40, and 48. Wow, okay, it seems like a very elaborate exercise. It seems very fun though, so I think we're gonna probably have to add this one, because this is what I really do is I read the textbook, and then I go, which exercise do I wish I knew how to do, and those are the ones I choose. I usually don't have the time to actually sit there and do them, but to start your program, okay. Time how long it takes. How long would you expect your program to take for SHA-512-256, for SHA-512-384, for SHA-512 itself? So, aren't we saying here that the more you truncate, the more difficult it would be to find a collision? And so what I'm assuming what this is saying is that, if it took how long was it? That's cool. Like, and this is obviously using the bench testing as well to kind of test these algorithms. But, here I think it's saying, okay, it would take you a really long time to find a collision here because you're truncating so much of the output. Here, you're truncating less of the output. Oh, wait. You're truncating more of the output here. So then it'd be even harder. We'd have less security. Okay, yeah, I'm already getting confused about truncating the output. Let's see. I thought it was... Yeah. This, you drop 32 bits here, right, is 512 with 128 bits dropped. Right. So if you use SHA-512 and you dropped 300 bits, you'd have 128 bits of security. And if you used SHA-512 and dropped that many bits, you'd have 256 bits of security. So you'd have more security here than here, I guess, even though that's very interesting. No, because you'd have 512 and then half of that. 120, oh my gosh. Okay, yeah, 128 bits of security is what you'd have. Right? And then here you'd have less. And then for SHA-12 itself, isn't the whole point that you'd have more collisions? Let me just read the question again. Consider SHA-512 minus n, where you're truncating off some n. A hash function that runs first runs SHA-512 and then outputs only the first n bits of the result. Write a program that runs a birthday attack to find an output on a collision on SHA-512n. I think the whole point is supposed to be that the smaller your n is, you have collisions, where n is a multiple between 8 and 48. So I would assume with 8, it's easier. With 48, it's more difficult. And then this is confusing to me, because I would assume this is supposed to be the easiest to find collisions. But I just have questions about this. So I think I'm just going to add this to the sheet because I want to at least know if I'm in the right direction with it. I feel a bit confused, if that even makes sense. For example, let me just take the note. So, does SHA-512, dash 256 have more security than SHA-512 384? So I would say yes, but then you're truncating more. So is that maybe you have more security, but it's harder to find the collision. So I think this is to where, yes, but maybe easier to find collision. But that wouldn't mean it's more security, right? So that makes no sense, right? So I'm just gonna put yes. I don't know. And then for SHA-512 itself, my main question would be does SHA-512, because this would be my example, dash n where n is greater than 0 have more security than SHA-512. So basically, even if n is 1 and you're only if you're only outputting 1 bit, n is, okay, wait, I'm understanding, you're not truncating. No, it runs SHA-512 and then outputs only the first n bits of the result. It's not, okay, write a program that, okay, so this is going to be easiest with the lowest number and harder with a higher number. So here we're saying if you're producing the first half, I would expect the larger one to have more security. But then they said you have collisions after a certain point. So let's just say no. Let's change that, and let's say that we're assuming that we're not truncating, we're outputting this much. I thought it was the other way around. Sorry, I thought I was getting a bit confused. And so, no, this is obviously not true anymore. Sorry, that's why this made no sense. You're only outputting n. So I would expect it to take, a good amount of time here, way more time here, and then a lot more time for the full SHA-256. Here you're just finding a collision with n bits? Yeah, just with n bits. So okay, so I feel like I understand the question a lot more now. It's not as confusing as I thought it was. And maybe it's not as, it seems like it's a good exercise for just writing a program in Rust for trying to find collisions in like 8, 16, 24, 32, 40, and 48 bits. And seeing how long it takes. That to me seems useful. So for the next one, let SHA-512-N be as in the previous exercise. Okay. Write a program that finds a message, M, a preimage, that hashes to the following value. Ooh, okay. So now we're trying to find specifics. This is cool. So I think this is actually going to be super useful because basically we're using the program from above and trying to alter it so that, you can find a collision for a specific message in 8 bytes, and then obviously it's telling you, okay, now you're using 16 bits for a message. Can you find a collision for this? Can you find a specific collision for this? Can you find I think these are all actually great. And then timing, how long the programs take, averaged over 5 runs. Your program may use this asynchronous library. How long should you expect? I think this is a great question. Again, especially because, this is not delicious. Wording that finds, whoops, let's at least try and do this. Write a program that does. Let's just at least get them from here. Right. Whoops. What do? Okay. And then this is a bit different. Time them. Yeah. Simple enough. Okay. Write a program that does this. I'm just trying to organize it a tiny bit at least. Okay, I really like the exercise, and I think anyone would learn a lot from doing that one. In section 5.2.1, we claim that two different messages both hash to H2. Show why this claim is true. Oh gosh. Sure. That's a good. Honestly, good exercise. I couldn't get there myself, to be honest, when they were going through it. So I'll put a little question mark beside this one to see if it's actually going to be added. The written work that that Thor did last time, it seemed like it took a little while. So, last question. Pick 2 of the Shaw 3 candidate. Okay, no, we're not picking that one because Shaw 3 is probably already completed. We'll probably just read about Shaw 3 anyways. So that was chapter 5. Question. I think these 5 questions are probably worth going through or trying to run through. In terms of the textbook, I will get the next one set up. So to I think it's like this CH6 max message authentication codes. Generally I do some random like a message authentication code or a MAC is a construct that detects tampering with messages. Encryption event prevents you from reading messages. Does not prevent the MAC comes in. Okay, we'll use the whole thing just to be cute. Usually I probably wouldn't put that. Oh, that's a bit much. Sorry. Oh geez, an hour and a half. Okay, I'm gonna finish this now. And then obviously tomorrow I'll try and come on and do some sort of stream. What a Mac does, and I'll start taking the notes, and we'll go through that. I do have to finish chapter 6 tomorrow. I do have to get the exercises up as well, and that actually seemed really short. GMAC, different HMAC. I went through the. Oh, actually, it's actually very short. I'll go through this tomorrow, and I should stream it and be done. The cryptography course on Coursera by Dan Bonet also has a lot of the same information updated and explained very clearly. So I do always go through that information first. I go through read the textbook, I take the notes, and I still find this all very complicated. I have a lot more math stuff to do and everything like that. But hopefully people might have found that helpful to kind of have someone walking them through it. For me, it's helpful. I do the talk. I have it read out for me. I try and stop and take notes of what I think is valuable. I have to go back and edit and fix some of these notes, but they're up there for now. And yeah, any comments, questions, concerns, just drop them in the comments to this video. And I hope the video worked. I didn't even check this time. So, deuces, I'm going to watch some Gone, Hunter x Hunter, probably, with the wife. And yeah, this is kind of fun. I definitely like this series a lot. Just kind of sitting here reading the textbook or having the textbook read to me. And going through exercises and all this. One of the ways, again, which I get to support the Uncloaked Study Group. I am in no way an expert, but I think that's kind of why I like showcasing this as well, that anyone can kind of take part and support in their own way.